Hello everybody and welcome to my presentation for Robotics 347 Robot Navigation at the University of Advancing Technology. So for this experiment, or this assignment I should say, I had to basically, um, we had to do something a little different than the original assignment because of a part shortage. So we were supposed to do air propagation with it, but what I wound up doing is I wound up doing that, but I had to think outside the box to do it. So what I did is I came up with an algorithm that would drive a robot forward, and while using an ultrasonic distance sensor. And if it started sensing an object that was coming near it, say between 12 inches and 4 inches, it would go into a caution function, which would slow the robot down, and it would generate a yellow LED light symbolizing that there is something in the way, so we should slow down. Um, and then if the ultrasonic distance sensor senses that the object is at least 4 inches or less, then a red light is going to appear and the robot is going to stop. Then the robot's going to basically, it's a state machine. What happens next is the robot is going to pause for a couple of seconds. Then it's going to go in the reverse direction. It's going to back up for a couple of seconds to try to clear the object. It is going to turn in a left-handed turn. I have it set up to make a 90-degree turn, and it was just by luck that I was able to do that. I used a tangent of 1 for a 45-degree angle, but because of the speed and a couple other factors, it turns itself into a 90-degree turn, which is really what I wanted. And then it jumps back into the forward position, and a green light goes on, symbolizing that everything is clear, and we're going to go into the forward position, move forward until something becomes within the distance of 12 inches to 4 inches. It'll slow down, and then it will stop and do the turn over again. So here's how I did the code for that. And it works really good. Just to let you guys know, it works pretty good. There are some slight deviations in the turn, um, but I plan on correcting that using a gyroscope in the future and writing a short algorithm that says that if there's a deviation in this between such and such of a degree, then we're going to point the autonomous robot in the right direction and go from there. Not hard. I already did it in another example, but I am pressed for time with this assignment, and I wanted to get something that was definitely working rather than handing something that worked a little bit, you know. So I uh, I would say this is a success. It works pretty good, I think. So here's the thing: to invoke the light, the LED, the RGB light on it, we have to include the Adafruit NeoPixel header file because there's a NeoPixel RGB on it, and that's how we do that. I have a couple of integers. I call them trigger and echo, and this is on pin 13 and 12, which are the dedicated pins for um, the ultrasonic distance sensor because it uses, I believe it uses an interrupt or an interrupt for that. The LED is on pin 4. How many lights we have is 1. I have an integer duration and an integer distance, and that's going to calculate. In the end, it's going to basically take the speed of sound and do some mathematical computation to that and spit out a distance in inches. So we basically set up the LED light here. These defines are going to define the pin numbers um, to specific things in the robot. So in other words, pulse width modulation, standby for the motor, stuff like that. I set the pin modes to outputs except for the echo pin, which is an input. And then we start the serial bus. So in a loop, it's actually not all that hard. So what I do is the first thing we do is we clear the pixel light, make sure that all the colors are off. We turn the trigger pin on. We wait a second, turn it off low. The reason why we do that is we want to measure the distance of that frequency, basically, when it leaves the distance sensor and when it bounces back. We call that duration, and it equals the pulse in, which is the echo on high. So basically, here's what happens. We set out a very high frequency, and it returns back to the robot. Okay, we take the time that it took for that to happen, divide that by 2. We take the outcome of that and divide that by 74, and we get the distance in inches. Pretty cool, huh? So that's how we're doing that. So in the main function, I use a for loop to iterate through the number of pixels or the number of LEDs, which is only one in this case, but the Adafruit library actually is pretty neat because what makes it so unique is you can control a bunch of LED lights using only a couple of pins. So that's what makes it so interesting. But in order to do that, you have to use a for loop. So I have to work within the parameters of the library that controls this particular LED light, if that makes sense. Anyway, knowing that, it's really basically a state machine. If the distance is greater than 12, then we're going to set the light to green, and we're going to turn the light on, and we're going to print on the serial bus, which you're not going to see right now, that it's going forward, and then we call the forward go function, which basically sets the robot moving forward. Now, if the distance is less than 12 inches and it's greater than 4 inches, then we know that there's an object that's coming into the range of the robot, so we're going to slow down to half speed. Set the color of the light to yellow to signify that there's something in the way, and we're using a cautionary measure to slow down to a safe speed so we're not going to run into it. Okay, so I'm thinking, autonomous vehicles here, such as smart cars and stuff like that. It will signal to the serial monitor that it's going forward in caution. So then if the distance is less than or equal to 4 inches, then a red light turns on and we initiate a robot turn maneuver, which is a series of functions, which is going to stop the robot, turn the red light on. It's going to wait a predetermined time. Then it's going to back up to give itself enough distance from the object to make the next maneuver without running into anything. Then it's going to make a 90-degree left turn and then go forward. And then it's going to repeat the process again. The light is going to turn green and it's going to go forward. And then if it senses something else, it's going to move into the cautionary position or the cautionary function. It's once the object gets into a distance that we deem dangerous, it's going to stop and execute the turn maneuver again, and it's going to do that indefinitely. So that's pretty much it. It works pretty good, but how we do this? So we're using an H bridge, and we're using 4 motors on this particular H bridge. 2 of the motors on the left, 2 on the motors on the right. They're both activated. Both sides are activated by a standby, which is either set to high or low. That's going to provide power to the H bridge and the motors, and it's going to turn the motors on basically. We set pulse width modulation to control the speed, 0 to 255 in this example. So I have it running at about 125, which is right around half speed, which is a safe speed for this assignment because the robot at 255, it does have a lot of torque and speed. And I'm working in a constrained environment, so I wanted to make sure it was safe to begin with. Then right here we have an A and B in, which is going to control each side of the robot. So A is going to control the left side, B is going to control the right side. If we set them to high, they're going to move forward. If we set them to low, they're going to move in reverse. And how we do our turns for this assignment is we basically pivot along the z-axis by having one side of the wheels move forward and the other side move in reverse, much like a tank. So we get a lot more precise turns that way, rather than using speed as a modifier between the difference of the left and right side to make a turn, which is going to make more of an arc rather than spin around its axis. Okay, so we know that. Okay, so with forward caution function, we go high, but we cut the speed even more down to 25% power, basically. So it works good. Robot stop, basically we set pulse width modulation to 0, and we set the standby to 0. Reverse, we basically just set the A and B inputs to low, and it will trigger the motors to run in reverse. Turn left, we set the left side to low, which is going to go in reverse, and the right side to high, which is going to run forward, so it will turn to the left. Now, to initiate the robot turn, we call those functions. Stop, wait for 3 seconds, reverse for 2 seconds, go left. We delay this for 1 second because, remember, I'm using a tangent of 1, and we're using time as the unit of measurement. So 1 second is going to give me the desired turning radius that I need. It works. It works amazing. So without further ado, I will show you the live part of the demo. And guys, I had a fantastic time with this. It was a fun journey. You guys have a wonderful day. Thank you. Okay, so for this experiment, I've had this robot running for quite some time now, going through its algorithm. And basically what it does is it'll drive forward. Once it's in the forward position, the light is going to turn green. Here, you'll see that. And then once the ultrasonic distance sensor senses something between 12 inches and 4 inches, it's going to slow down and the yellow light comes on. So it'll keep going forward at that time, and then once the distance sensor reaches an object that is 4 inches or less, the red light turns on, signaling a stop. Then it's going to go into its turning maneuver, which is going to back up for 2 seconds, turn at basically a 90-degree angle. Actually, I calculated it out for a 45-degree angle using a tangent of 1, but the speed of the robot takes into consideration of that because I'm using time as the unit of measurement. And so basically what it does is it boils down to 45 degrees twice, and it produces basically a 90-degree turn, which is really what I wanted. So once it does that, it goes back into the turn. Sorry about that. He kind of got out handed a little bit. Anyway, as you can see, it needs a little bit of work, but it is working. So for future reference, I'm going to incorporate a gyroscope. Hold on a second here. Let me grab this thing. Let's try this again. I'm going to incorporate a gyroscope to see if I can get a little bit more precise measurements out of this, because although the forward position or the forward function and the caution function works very good, the turns sometimes are not exactly what I want. There's a deviation in there, so I know I could put an algorithm in there saying that if it deviates this much, then turn back to this, that type of thing. So it works. It's working actually a lot better than I thought. So we'll watch it a couple more times and then we'll call it a night. I really do get a sense of accomplishment when something works out like this. Yeah, it's definitely working. That's kind of... All right. We'll end it here. Anyway, guys, thank you very much for watching this presentation. I do appreciate it. I can't get enough of this. I just love it. It's fun. All right. Bye-bye.